Okay, so today's class is the final material that is fair game for the upcoming test, right? So we have a test on Thursday. Wednesday's class will be a review for it. And then Friday, we kind of get right back into the new stuff again for the midterm. But if you haven't seen it, we do have here a kind of more detailed post about what will be on our test. It's basically a double length quiz. So expect roughly, twice as many questions as we've seen on the quizzes. It's restricted. It's only open from 7 to 9. So make sure, again, just like we mentioned, the beginning of the semester with the syllabus talk and all that sort of stuff, have these, dates for the exams and whatnot in your calendar. Yeah, otherwise, treat it as a longer quiz that's worth more points. So make sure you put in a few extra hours or so of study time before you come to this. All right. Oh, I guess if I keep going down, I should mention as well, right, the web work due date for the payments or whatnot is coming up. So this is open, but yeah, September 20th at 10 a.m. If not, you get temporarily locked out, and once you pay, your account gets restored and all that sort of stuff. But again, I would take care of that sooner rather than later. It's a kind of a pain, if you get locked out and then the getting your account restored doesn't happen immediately. It takes like an hour or two or whatnot. So I would recommend that take care of that sooner rather than later. Yeah, I think that's the main administrative stuff. Questions though? Any questions about anything about the class, especially with the test coming up? Yeah. Yeah, so I mean, the standard quizzes are 30 minutes long, and so the test is 60 minutes long. Yeah. Good. Any other questions? All right. Well then, why don't we go ahead and get into the math for today? Our end goal today is that we'd like to talk a little bit about parametrized surfaces. And ultimately, kind of this section right here is a nice segue into what's coming after test one, when we will be talking quite a lot about various surfaces and whatnot. And so, as you learned in Calculus 2 and maybe even before that, besides the Cartesian coordinate system, the classic x's, y's, and z's, there are other systems that we can use in order to describe surfaces. And so in the pre-class videos here, we talk a little bit about cylindrical and spherical, which are two different upgrades from polar coordinates from our 2D systems, right? So one way that you can upgrade polar is that you literally just do the exact same stuff as you would in polar. So with x's and y's, these are the exact same equations that you saw in Calculus 2. And then you just say z is going to be what it is. And it turns out if you need to describe various cylinders and things like this, this is a very useful coordinate system, and hence the name cylindrical coordinate system. So you get a lot of the equations and whatnot that you know and love from polar here. So a lot of these probably seem familiar. These do show up on the formula sheet as well. I think they're maybe on the second page, but you don't have to have these all completely memorized and whatnot. So again, especially with the test coming up, I would really advocate for printing off that formula sheet, carrying it around with you between now and then, and making sure you know exactly what's on there and what's not on there, so you know what you need to memorize or put to memory versus what you don't. Another reasonable way that you could upgrade polar is by throwing in one more angle. And it turns out this is really great for like mapping spheres and stuff like this. So again, kind of you have the classic theta from polar. This is how much off of the x-axis you would like to be. So this is the exact same theta as you have from polar. But then rather than, x's and y's and stuff like this, we're going to describe maybe an angle off of the z-axis. So this kind of controls your up and down, right? The theta is going to do the left and right stuff. But the phi is going to control up and down. And then rho is basically a three-dimensional radius. How many steps off of the origin in 3D do you want to take, rather than r being a 2D radius? Again, there are a lot of algebraic equations that you should know, right, that are very useful in order to translate between x's, y's, and z's and spherical here. And so we did a little bit of that. We'll do even more here in the during class portion. But that's kind of the cylindrical and spherical in a nutshell. And like I said, we'll also talk a little bit about generalized parametric surfaces as well, which is kind of most closely related to what we're doing in chapter 13, where we have these parametric curves, right? We have these vector functions and whatnot. So basically, we're going to be upgrading that. Any questions on the pre-class stuff? It's been a long time since I've gotten a question when I ask for this. I feel like these aren't explained perfectly. You should have a question or two every once in a while. So, please do, if there are any questions, make sure you ask during this part. So, okay. But why don't we go ahead this time and we can move on to the new stuff. So let's see this one here. So yeah, in the pre-class stuff, again, we converted from Cartesian to cylindrical to Cartesian, back and forth. We also did Cartesian to spherical. So we're going to get a little bit more practice. And this time I'd like to convert spherical into Cartesian and vice versa. So why don't we go ahead and start with this Cartesian point. And I would like to convert it first into cylindrical and then into spherical, just kind of as a nice review here. So again, for Cartesian, these are, wake up. Again, I'm borrowing a stylus. I feel like I may be doing something wrong. Okay, I got it, guys. All right. No resting the palm is the key here. All right, so yeah, X's, Y's, and Z's. And I'd like to convert this first into cylindrical coordinates, which means that I need an R, I need a theta, and I need a Z. Now, in cylindrical, Z is the exact same as Cartesian. So whatever Z was, we can just copy and paste here. So that's quite nice. However, for the R's and the thetas, we need to convert. And we're going to use the exact same conversions that we did back in your polars stuff, in calculus 2. So one of them here, for R, for instance, we can look up and see in our conversion equations that we have that x squared plus y squared is equal to r squared. So this is the conversion equation that we're going to utilize in order to transform from our x's and y's to our r's. So in this case, let's see, we have root 3 over 2 squared plus negative 1/2 squared. And let's spend a little bit of time simplifying that. So it's going to be 3/4 plus 1/4. So that all very nicely works out and is just 1. And supposedly this is supposed to be equal to r squared. So that means when we solve for this, r can either be equal to 1 or negative 1. Plus or minus technically works. However, again, we're going to be getting to a point where we're going to be integrating. We're going to be doing a lot of things with this, and we don't want to kind of double count our points. And so we're going to restrict down in Math 234 to positive radiuses. This will just ensure that we're counting our points once and only once. So although there are multiple ways to describe this, we're going to stick with positive radiuses in this class. So that's why we restrict down, and we're only going to use r equals 1. So although there are multiple ways to describe this in our class, we're going to stick with positive radiuses. Okay, now we need to go ahead and figure out a good way to convert our thetas. So according to our equation here, we have that tangent of theta is supposed to be equal to y divided by x. So I can take my y coordinate and my x coordinate and plug these things in. So I'm going to get negative 1/2 divided by root 3 over 2. Those were my x's and my y's. And this is supposed to be equal to tangent of theta. So this is what we need to solve here. Well, I do notice that we could multiply through by 2 on top and on bottom here and kind of cancel out these 1/2s. And then at this point, there's kind of a variety of reasonable ways that you could take this. You may recognize that this is, in fact, on the unit circle, either as it is, this negative 1 over root 3, or maybe if you go ahead and convert, it may be more common to see like negative root 3 over 3. But if you know your unit circle for not only sine and cosine, but also for tangent, you'll recognize that in this case, theta is equal to negative pi over 6. So I would expect you to maybe at least know this for the positive, right? It would be positive pi over 6, but since it's negative, it's just going to be negative pi over 6. So this would be a reasonable answer here for our theta. Now, quite often in our class, we do restrict down and like our thetas to run from 0 to 2 pi, so to be positive, right? And so if you'd like to, right, remember the thetas are cyclical, they just keep on going around and around and around. You can also say that this would be like 11 pi over 6, right? If you add 2 pi to that, that's one full rotation. This would also be a legitimate answer. So in cylindrical coordinates, if I decided to write the order with r's first, and then thetas, and then z's, the point would be 1 negative pi over 6, and then root 3. So this would be one completely reasonable answer. But again, it's not the unique correct answer. If someone wrote 11 pi over 6 here, this would also be a correct answer, right? So we have to accept multiple correct answers here. You can also, right, let's say if you don't know that this is negative pi over 6 off the top of your head, right? You could, in your TI-30 calculator, or TI-83 or TI-84 or whatnot, right? You could apply a tangent inverse to both sides. And if you apply a tangent inverse to both sides, right, it's very possible that you'll get some decimal. And then you could check, right, the common angles on the unit circle. You could check pi over 6 and pi over 4 and pi over 3. And if any of those decimals line up with tangent inverse of negative 1 over root 3, then you know that that's the answer, right? So that's a good way to get around this, even if you don't have your unit circle completely memorized for tangent. All right, any questions on this one here? Okay, well, let's go ahead and convert then into spherical coordinates. So for spherical coordinates, again, the nice thing here about spherical is that it shares at least the same theta. So the theta that you got from cylindrical is exactly the same theta here. So again, you can do negative pi over 6. When you're doing like, I've seen a decent amount of like the web work homework and also like quiz and exams sometimes say, you know, have your answer be between 0 and 2 pi. So you need to know that this is equivalent, right, to having 11 pi over 6. So this may even be a better answer. It'll be accepted by, you know, the web work. And sometimes if we say this restriction on D12, you know, this is the answer that it's going to want. All right. So that's the first thing here. But we still need our rho and our phi. So those are the other two coordinates that we need for spherical. So again, you can kind of go back to these conversion equations that we had in the pre-class notes. And again, they show up as well on our formula sheet. So maybe it's not a bad idea. We can grab this really quick and just show you. So I think the formula sheet, at least where I know it is under the quizzes. Maybe under the tests as well. But eventually what we're going to be doing with these things is doing some integration. So it's on the second page here. But notice before you even worry about, we're going to get to doubles and triple integrals and that sort of thing. But luckily that's not until chapter 15. But before that, you get these transformations, right? So there's our transformation equations for polar / cylindrical. And if we go to spherical, right, again, we have a set of transformation equations. So those are there and available for you on this test. So that's nice. Okay, and let's see, if I wanted to get rho, I can notice that I have this thing here, that x squared plus y squared plus z squared equals rho squared. So if I'm interested in solving for rho, maybe I could go ahead and use that equation there. So again, x squared plus y squared plus z squared should be equal to rho squared. So I have an x, a y, and a z coordinate already. So I can go ahead and start plugging those things in. So we could do root 3 over 2 squared, the negative 1/2 squared, and the root 3 squared. We already did this a little bit, right? We get 3/4 plus 1/4, and now we have the plus the z squared, so that's going to be plus 3. So this is going to be 4 altogether. And again, this is supposed to be equal to rho squared. Now we can take the square root, and just as before, we should get plus and minus 2. But just like I mentioned for R, our 2D radius, again, this is supposed to be a 3D radius, and we're going to restrict down to only positive radiuses in our class, right? So that way we count all of our points once and only once. So in this case, we're going to have rho is equal to 2. One more to go. We need to figure out what phi is. And so if we go back to our transformation equations on our formula sheet, we can see that there are a lot of these that have phi's in them, but unfortunately none of them have like phi equals, right? So all of these we're going to have to manipulate a little bit in order to solve. The one that maybe I'm most interested in, just because it's a little bit less work, is this one for z here, right? So now that I know what rho is, 2, and I know what z is, root 3, I can go ahead and plug these things in, and hopefully I can solve for phi pretty fast. So that's going to be my strategy here. So again, z, according to our transformation equations, is supposed to be rho cosine phi, and I'm interested in solving for phi. Now, from the statement of the problem, we know that z is equal to root 3, so we can go ahead and plug that in. And we just solved, did a fair amount of work to show that rho is supposed to be equal to 2. So now all we can have left here, right, is solving for phi. So, okay, luckily this can simplify to root 3 over 2. And again, this is one of these classics that are on our unit circle, right? So hopefully you know that, but if you don't, right, you can apply the cosine inverse in your calculator, you'll get some decimal, and then maybe you can kind of plot and do these different, pi over 6 and pi over 4 and pi over 3 and all that sort of stuff. But yeah, cosine is equal to root 3 over 2 exactly when phi is equal to pi over 6. So phi would be equal to pi over 6. And if you wanted to put this as an ordered triplet, we could do rho phi theta is equal to 2 pi over 6 and 11 pi over 6. All right, a little bit of work, but not too bad. Yes.
Theta, not rho theta phi.
So I wrote it here as rho phi theta, but there's not kind of a standardized order for this triplet. Like for x, y, z, everyone kind of agrees that x is first, y should be second, z should be third, right? And so they don't need to specify it every single time they write an ordered triplet, right? Because that's the established order. But in this case here, there's not really an established order. You can see, at least I'm consistent with myself, and I have rho phi theta here, but there's probably other places where I've written where I did switch the order, or even in a textbook and stuff like this. And so they may do rho first, theta second, right, and then phi third. But there's not kind of a traditional ordering like there is for Cartesian. Yes, back here.
Same equations. Is it going to get more complex than that?
We'll see that you need to be sometimes a bit more clever, but you're going to be using these same equations, right? When you're transforming between these coordinate systems, you're going to be using those same equations over and over again. Yeah. Okay, well, I have one for you guys to try. Imagine that this is a true-false question that shows up on your exam, your test. I have a rho, a phi, and a theta given to us, and my question is given, right, the product, x times y times z is positive. Is this true or false? So please take 60 seconds, 90 seconds. Identify for me if this is a true statement or a false statement. All right, let's start talking about this one together. Again, ultimately, this is a transformation question, right? You're given something in spherical, and you want to know about the coordinates x, y, z in Cartesian, right? And so it'd be very useful if we could convert from spherical into Cartesian. And so again, if you go onto your formula sheet and you look at what are my transformation equations, you'll identify that there are ways that you can get x, y, and z if you know what rho, phi, and theta are, right? And so I've written those down here. And ultimately, right, we're interested in this product, is it positive or negative? So we're going to be multiplying a bunch of things together. And the question is, are they positive or negative at the end of the day? So, right, for instance, when I plug in rho equals 4 in this case, I mean, that's nice and it's a perfectly good number and everything, but ultimately it's positive. And then next up, I'm going to go ahead and I'm interested in sine of phi. So it looks like phi in this case is 5 pi over 7, right? So again, we could use our calculator for this and plug that in, but I know that it's less than pi. So sine of something less than pi here is going to be positive. So again, it's a perfectly good number that you would get out in your calculator, but the big thing here is that it's positive. Next up, I need cosine of theta. My theta value is supposed to be 3 pi over 4, right? So we can think about this as in the second quadrant here. Cosine in the second quadrant is going to be negative. So ultimately, my x is going to be positive times negative. So overall, my x is going to be negative. Again, you can figure out what the exact number is, and that's another legitimate way to go. But whatever it is, it's negative. And since this is only a question about is it positive or negative, then we can just, talk about that, the sign of this. And we can play the same game again, right? We can go for our y's. Rho is going to be 4, a perfectly good positive number. We're going to have sine of 5 pi over 7, which again, a nice positive number. And then we have sine of 3 pi over 4. So altogether, y is going to be positive. Positive times positive times positive. And then finally, for z, rho is 4, a nice positive number, and cosine of phi. Well, again, 5 pi over 7 is in the second quadrant. Cosine in the second quadrant is negative. But if you don't happen to remember that, that's fine, right? Your calculator will verify for you. Should have it in radians mode, but when you do cosine of 5 pi over 7, it will output a negative answer. So we are interested in the product x times y times z. So I have a negative times a positive times another negative. So the overall, it is going to be positive. So the answer here is going to be true. So this is how we can embed, a conversion equation like this into a true-false. Any questions on this one here? Yeah.
Work on the exam for a problem like this. Is doing what you did enough work to write it all?
So yeah, the question is about what kind of work would need to be shown. Well, so if this was a true-false question on the exam, right, then there's no partial credit given. And so it's just kind of enough information so that you can kind of make sense of it yourself, right? And so this would be, more than enough work. I mean, at the end of the day, if you have a lucky coin and you flip it, right, and it comes out true, and you guess that, you get the full points when it comes to multiple choice or true-false style questions, right? It's only on the standard response questions that you have to show your work, and then we grade those for partial credit and all that sort of stuff. All right, good. Any other questions? Well, I think that's enough maybe then converting points. Let's go ahead and start converting full surfaces. So I have this surface equation. Notice that there are x's, y's, and z's in it. So this is in Cartesian. And I would like to go ahead and convert this first into cylindrical and then into spherical coordinate system. So in cylindrical coordinates, remember I win the game once I have no more x's and y's, but there should be r's, thetas, and z's. So the fact that I have a z on the left-hand side, I'm perfectly happy with that, right? So on the left-hand side, I can leave that as z. And again, I need to only have r's and thetas at most, right? And so I can go back to my transformation equations, and I'll notice that one of them says that x squared plus y squared is supposed to be equal to r squared. So I can go ahead and trade that in. Everywhere I see that x squared plus y squared, I'll put r squared. Now, this is technically here the absolute value of r, if you'd like to simplify. However, again, in our class, we're only going to be using positive r's. And so that means the absolute value here is not really doing anything. And so we can just write this as r. So z equals r would be the correct equation here. Now, if you wanted to, although it takes a little bit longer, right, we also have that x is supposed to be equal to r cosine theta, and y is supposed to be equal to r sine of theta. You could instead swap those in for x and for y, and then you square them and add those together. And if you factor out the r squared, you'll have cosine squared plus sine squared, and that equals 1. So either way, you can simplify it down to the same answer, no matter which path you take. This one just happens to be a little bit faster if you switch out the x squared plus y squared directly for the r squared. All right, how about in spherical coordinates? Well, in spherical coordinates, and I mentioned this in the pre-class video, but it's not on our formula sheet. So this is kind of one of these things that I would recommend that you have put to memory. One of the formulas that's not on the formula sheet is that r is going to be equal to rho sine phi. And in fact, you see that in the transformation equations, right? When you kind of go from cylindrical to spherical, right, that r is equal to rho sine phi. I think that this is another useful one. In fact, if I got one more equation to put on the formula sheet, in this transformation section, I would recommend this one here. So I have this one memorized. And so this becomes very useful, right? Because then instead of starting with my z equals here and converting that into spherical, I could start then with my cylindrical. So if I'm starting with cylindrical, well, I know that z is equal to rho cosine phi. And my claim is, if you know this equation here, then, well, z is supposed to be equal to r. And if r is the same thing as rho sine phi, that's quite nice, right? That's pretty simple looking. Otherwise, right, you're going to need to plug in for the spherical stuff for x being rho sine phi cosine theta, and for y rho sine phi sine theta, right? And then trying to simplify that down, and you'll get the same result, but it'll just take you a few extra steps. So at this point, this is technically in spherical coordinates. However, it can be simplified more, right? And so why don't we go ahead and simplify this? For instance, so long as rho isn't exclusively 0, we can cancel it on both sides. Now, phis here, right? Phis typically range from 0 to pi, right? Thetas usually range from 0 to 2 pi. They go all the way around. But phis, remember, go from straight up to straight down. So phi equals 0 is pointing straight up. Phi equals pi is pointing straight down. So they go from 0 to pi. So while theta has the full range of 0 to 2 pi, phis have the range from 0 to pi. So thinking about only from 0 to pi, do we know a place where sine is equal to cosine? Think so? Yeah, do you know here? Pi over 4, yes. So this means that the simplest way that you can write this is phi equals pi over 4. So this is kind of thinking about it a little bit more ad hoc, right? And trying to come up with a solution and thinking about the unit circle. Of course, if you like more of a systematic approach, you would say, well, maybe I'm going to go ahead and divide by cosine on both sides. If I divide by cosine on both sides, well, then on the left-hand side, cosine divided by cosine would be 1. And on the right-hand side, sine divided by cosine would be tangent. So this kind of consolidates all of your phis into one place. Now, again, you could ask the question, do you know a place where tangent is equal to 1? And some of you may remember from the unit circle, right, that, yeah, at phi equals pi over 4, you have tangent equaling 1, and that would be completely legitimate. Or, right, you could do tangent inverse of 1 on your calculator, and it'll give you some decimal, right? And then you could look at the common angles, pi over 6, pi over 4, pi over 3, pi over 2, right? And you'll notice that the decimals for pi over 4 exactly line up for the decimals with tangent inverse of 1, right? And so therefore, you would get the same result. So there's a couple of different ways that you can get our final answer. So again, in spherical, this is as clean as you can write our equation, right? Again, it's only supposed to have rhos, phis, and thetas. In fact, we were able to simplify this down so there weren't even any rhos or thetas. It's just a nice phi here. All right. Any questions on this problem here? Yeah. So the question is, on a test, could you leave it as rho cosine phi, rho sine phi? With these instructions here, convert it into spherical coordinates? Yes. If it was to elaborate farther, if it was to say and simplify as much as you can, or if it was a multiple choice style question, right, where that's not an answer, but maybe phi equals pi over 4 is an answer, right, you would have to know to keep going farther. So if it's written exactly as it is here, yes, you could leave it as soon as you've gotten rid of x's, y's, and z's and only have rhos, thetas, and phis, right? That's the first place that we're really into spherical. Good. Any other questions? Well, I have some multiple choice problems for us here. Maybe I'll do the first one, and I'll let you guys do the second one. But I've set these up pretending that, you know, again, almost a multiple choice style for a quiz or an exam or whatnot. And I've written them as identify the surface whose equation is, and the first one, it looks like it's in cylindrical. And the second one, it looks like it's in spherical, right? So this first one has z's and r's. It doesn't happen to have any thetas, but I don't see any x's and y's. And the second one, right, rhos and phis and thetas, right? So that one's definitely in spherical. So when I see a question like this, I think about, okay, I've learned to identify surfaces quite a bit in like 12.5 and 12.6, right? I kind of know the equation of what a plane should look like. I know the equation of what some of these other, right, the elliptical paraboloid, hyperbolic paraboloid, cylinder, right, that sort of stuff. I know what those equations look like in Cartesian, right? But sadly, these are not in Cartesian. So again, really, this is a conversion problem. If I could convert these into Cartesian, then maybe I could solve that exactly like I would in 12.5 or 12.6. So if I go ahead and spend a little bit of time converting, maybe this first one here, z is equal to 4 minus, and again, I know what my graphs look like. I can kind of use these things, I can graph these things a lot better if they're in Cartesian. So I'm going to swap out and I'm going to make it in Cartesian, right? So I've learned for cylindrical that r squared is equal to x squared plus y squared. So this would be equivalent to, bless you, 4 minus x squared, sorry, 4 minus x squared minus y squared if we wanted to go ahead and distribute that out. So then just like I did in 12.6, right, I could go ahead and plot a few traces, a few cross sections, you know, when x is equal to 0, when y is equal to 0, and when z is equal to 0. And when x is equal to 0, I'd have 4 minus y squared. That's going to be a parabola. When y is equal to 0, I'm going to have 4 minus x squared. That's also going to be a parabola. That 4 shifts it up, so that's the shifted up there. And when z is equal to 0, I could rearrange this, and I'm going to get a circle of radius 2. So if I was to combine all of these things into a final picture, right, we have parabolas and we have a special ellipse. It's a perfect circle in this case. So I'm looking for something with ellipses and parabolas, right? And it turns out B would be my correct answer. So this is a great kind of question, right? Because not only does it test the conversion stuff, but it also tests the 12.6 stuff. All right, so maybe let me give you 30 seconds, 60 seconds, work on the second problem here, which is in spherical. I have rho equals sine phi sine theta. And again, I'm trying to figure out what is the surface like. I don't know really surfaces in spherical yet, but I know them in Cartesian. So if I could convert this into Cartesian, I stand a chance. That's what you should be kind of thinking to yourselves. All right, let's talk about this one together here. We got the question a little bit earlier, right? You know, are we going to be always using the same transformation equations? And I think this is a good example where the answer is yes, but sometimes you have to be a little bit clever with them. And so when I personally see this, I see sine phi, sine theta. And that's close to one of my transformation equations, right? On the transformation equation stuff, we know that rho sine phi, sine theta, can actually be converted into Cartesian pretty nicely. What is this equal to? Y, right? So if only I had an extra row on the right-hand side, then this would just be y, and life would be grand. Well, of course, mathematically, if I don't want to ruin the equal sign, whatever I do on the right-hand side, I need to also do on the left. So if I want to multiply my right-hand side by rho, I should do the same thing on the left-hand side. But again, kind of this is me being clever with these transformation equations and identifying, okay, this isn't exactly what I know how to transform, but it's close to it. And then how do I, make up that difference? In this case, well, I need to multiply by rho. We get a little bit lucky here, right? Because while multiplying by rho on the left-hand side also lines up perfectly with one of our transformation equations, right? Rho squared is supposed to be equal to x squared plus y squared plus z squared. So now at this point, I have this completely transformed into Cartesian. So, well, here you could either venture a guess, right? Depending on how your time's doing, imagine that this is on a quiz or an exam or whatnot. You could either venture a guess or you could kind of spend as much time as you'd like to kind of make sure that the answer is the way it is. And so I believe that maybe looking at that x squared plus y squared plus z squared, I'm leaning pretty hard towards that this is some sort of ellipsoid or sphere, right? Certainly x squared plus y squared plus z squared equaling like 1 or something like this. This is the classic unit sphere. Turns out this is indeed a sphere, but it's been shifted over, right? So we would need to complete the square here. Turns out the right thing to add is 1/4, by the way. So if you really wanted to spend a lot of time on this, you could complete the square and then really get this into its standard spherical equation here. So you could really see that this is just a sphere that's been offset by a little bit. But yes, this is going to be a sphere. And so the answer for this one is going to be E. Any questions on this one? All right. Well, in the interest of time, I do want to spend maybe quickly here thinking about, you can graph these things into cylindrical or in spherical, and how you would do this. So thinking about this again, maybe with this z equals the positive square root of x squared plus y squared. If you were to square both of these sides, you would see the classic equation for a cone. Now this is only the positive square root was given to us. So that means that it's only the positive z values. So it's the top half of our cone. Remember, cones in calculus 3 typically have a top and a bottom. But because it was the positive square root, only positive z's, so it should lie above the xy plane. So this is going to be a half cone pointing in the positive direction. In order to graph these things relatively fast into cylindrical and spherical, looking at z equals r and saying, how do I know it's this shape? Or likewise, looking at phi equals pi over 4 and getting the same picture sort of deal. I want you to think really quick about, and we brought this up, back in chapter 12 a little bit, but when I'm graphing in our good old Cartesian, think about when I'm graphing y equals 1 and thinking about this in terms of restrictions. So again, in this case, y equals 1 means that x can be anything. There are no restrictions on x. And the way that x moves is left and right. So if there are no restrictions on x, x can be equal to 5, it can be equal to negative 13, it can be equal to anything it wants. But the only restriction is that y must be equal to 1. So when x is not a part of the equation, X basically runs free is what I'd like to think about it. And the way that X runs is left and right? It's the horizontal movement. So I'd like to play this same sort of game and thinking about when we're missing a variable, letting it kind of run free sort of deal. And notice that this Z equals R doesn't have any thetas in it. So if I was to graph this in maybe, I'm going to do just a half plane here. Remember, R's are only positive. We don't have negative R's in our class. So if I was to graph this in like an RZ half plane here, I would have Z equaling R. Well, that's just going to be a straight line. So the worst case is R equals 0, and then it keeps on getting more and more positive. And this is basically like a y equals mx plus b sort of situation. Slope is 1, intercept 0, right? I could write this as z is equal to 1r plus 0 if I really wanted to. And in order to get my 3D picture, notice that there are no thetas. So when there are no thetas, I can think about theta running free. Now, how does theta move? Theta moves, right, from the positive x-axis going around. We can think of it basically going around. Here's the x, here's the y. It basically circles around the z-axis. So when I allow my theta to run free, it's going to take my picture here and just copies of it around the z-axis. So if I was to go ahead and take that nice straight line and spin it around the z-axis, letting theta run free, you would get this exact same picture. This line just circling around the z-axis gives you the upper cone. So that's one way that you could graph this from cylindrical, right? Is again, notice that it's missing our theta. And so we can draw it first in the RZ half plane. And then in order to get the 3D picture, just let it spin around the z-axis. Yes, question. Z can be negative. So Z, right, so there's a negative Z-axis as well down here. So the half plane is only restricting R to be positive. But Z could certainly be negative. Sorry, one more time. If R is only positive and Z is equal to R, then in this particular case, Z is positive. But in general, it wouldn't be. Sorry, one more time. This one? So remember the problem that we were given in 9.9 was the positive square root. So the positive square root of x squared plus y squared. And so this was me doing kind of a fast drawing of, again, what was the cone that we graphed in 12.6. But notice that this is only the positive square root. And so it's only the top half of the cone. Does that make sense? Sorry, one more time. Oh, okay. I think you asked, why is this one positive? So why don't we also look at the spherical one really quick, and we can come back to it if there are more questions. So I'd like to play the same sort of game here, thinking about this RZ half plane. Now remember, phi is supposed to be the angle off of the z-axis. So if I think about drawing phi equals 0, it's pointing straight up along the positive z-axis. If I think about phi equals pi, it's pointing straight down towards the negative z-axis. In this case, it's supposed to be pointing at phi equals pi over 4. So that's 45 degrees off of the positive z-axis. There are no restrictions on rho, which means that it can go as far along this line as it wants, right? Rho is supposed to be the 3D radius. And there are no restrictions on theta. So again, if I wanted to get a nice 3D picture of this, I could go from my RZ half plane and let this run free, right, around my z-axis. That's the way that theta likes to run. X's run back and forth, left and right. Y's would run up and down, but thetas go around in circles, right? So I take this straight line, right, and I drag it around. And so again, we're going to get a nice cone. So we will do more of this, come chapter 15, but I did want to let you know that you can actually graph these sorts of equations in cylindrical and spherical as well without going back to Cartesian every single time. All right, I do want to use the last 2 minutes here, I'm sorry to say, and at least kind of bring up this notion of parametric surfaces. A lot of the stuff that we're doing with parametric surfaces here are just converting points. So we're just going to be converting points. And so I go into this a little bit of detail, right? So in the special case of parametric surfaces, right, we could let R be equal to R, theta be equal to theta, and Z be equal to R, for instance, in this last case. And then we could come up with a set of parametric equations based on the parameters R and theta. So again, for parametric surfaces, you are going to be plotting surfaces. So these are two-dimensional objects. They should have two variables. So just like when we did curves, these are one-dimensional objects. They have a length, right? You just have one variable, R of t. But here, when you're doing surfaces, you're going to need two variables. So in this case, right, maybe we could parameterize with R and with theta. So if I wanted to come up with a parameterization, X is going to be R cosine theta. Y is going to be R sine theta. Oops. And Z, well, Z was supposed to be equal to R. Many times in the textbook and whatnot, and in web work, we don't like to use, especially double using R there, one being a vector function and one, being a variable. It's a little bit clunky. And so quite often we use S and T, right? So rather than those variables, R's and thetas, S's and T's, the other nice thing is that our keyboards have S's and T's. We don't have thetas. So S cosine T, S, oops, sine T, and then S. So this would be using the variables S's and T's rather than R's and thetas. But again, kind of eventually, all this is really going to come down to, you'll see in the web work as well, at least for right now, is that we'll convert points. So I'll give you an opportunity to think about this one on your own since we are out of time. And then again, I'll post the solutions to this on D2L by 4 o'clock. So, all right, I'll stick around if there are any one-on-one questions. Otherwise, I hope you guys have a great rest of the day. And good luck studying for the test and everything. And I'll see you guys on Wednesday. We'll have a review day.